Arun sir. Arun sir.
Shall we start, sir?
Yes, we can start. Sir.
All right.
Good evening, everyone. Akash, or a small intro after I shall start.
Yep, sure. Go ahead.
Okay, right. Good evening, everyone. On behalf of Karpam College of Engineering and the Department of Mechanical Engineering, I welcome you all for the day 4 of the Faculty Development Program on Advanced Manufacturing Technologies. Today's session will be handled by Mr. Akash Shivaprasad. He is an alumni of Karpam College of Engineering, and he has pursued his master's in University of Buffalo in the Department of Industrial Engineering and Advanced Additive Manufacturing and Prototyping Technology. He has served as an industrial design engineer in bioprinting and R&D department for a period of 11 months, and currently he is holding the position of senior industrial design engineer at 3D Systems Corporation. It is an honor to have you at for this faculty development program, Akash. Now you can take over. Thank you.
All right. Thanks for the intro. Yeah. So this session is just like a 101 on 3D printing or additive manufacturing. So I'll be just going brief on where it all started and the different technologies and how the whole thing is going to like be in the future from now. Yep. So moving on to the next slide. Yeah, so that's like the overview of what the presentation looks like, and let's get started. So, all right. So what's 3D printing? So I assume a lot of you are using paper printers like almost every day. So that's you have a text material or a 2D file, and then you just print it on paper. So what if we can do that over and over again with same registration, so that you end up getting a 3D model? So that's what 3D printing like is about. So what do you do is say an engineer comes up with a CAD model of something. In this case, it looks like a diamond. So if he wants to like see how it's going to look as a final product, so what he can do is he can print it. So he doesn't have to visualize it or see how it would look like or make drawings, which again is a 2D representation, which makes it a little hard to make all the design decisions. So what he can do is once he has the CAD model, he can slice it with certain software. So what slicing is you take your CAD model and then you just pass a thin razor blade through it, taking down like section by section, and yeah. So that the height in which you slice is completely tunable. It also depends on the printer and the technology that you print on. So once you have that, you can pass it to a printer, which again like takes that information and translates into a 3D object layer by layer. So that's what 3D printing is, if you put in a layman's terms. So yeah, the whole thing started around like in 1980s. So there were two technologies competing. So one is stereolithography or SLA, which is you take a liquid vat of a photopolymer and then you make a 3D object out of it. And the next technology is you have a spool of plastic filament made of any material that you want, and then you just guide it through a certain process and procedures and layers to end up getting a 3D object. So those two are like extremely key milestones for 3D printing. And the former, the SLA, was invented by Charles, who's my boss, in fact. So yeah, I work at 3D Systems, and the competitive technology, which is called FDM or Fused Deposition Modeling, is run by Scott Crump. So he has a separate company called Stratasys based out of Minnesota and Israel. So that's what it looked like in 1980s. So from there, the whole journey is taken the technology so far and like kind of maxed out on what it could do. So in general, 3D printing, or yeah, if you ask anybody what can 3D printing do and like what all technologies that you have, it's generally going to fall into 4 to 5 categories, depending on what you want to achieve. So the first thing, or like the most common thing, is the fusion deposition modeling, which is, again, I told you, like you have a spool of plastic filament, and then you just extrude that out to a platform, and then like build your 3D object. And the second common one is the stereolithography, which is you have a vat of photocurable resin, and then just keep polymerizing it layer by layer, and then finally you end up with a 3D object. So these two are like the most common out there. And the third one is it's called material jetting, which is it's analogous to an inkjet printer that you see in your office or anywhere. So what it does is it has a jet which can jet out polymers at specific intervals and timings and drop size, so that as it passes back and forth, you do a 2D printing over and over again, so that after X amount of time you end up with a 3D object. And the fourth one, or kind of little industrial grade, is selective laser sintering. So what that does is you have a big chamber of powder, usually plastics like nylon, but there are metal powders too involved. So you have a super high powerful laser that then like kind of rasters around the block where the powder is being held, and that is done layer by layer to end up getting a 3D object. The fifth one is it's a technology that's still in development. So Xerox and Vader Systems, these are like two companies who were kind of, Xerox was pioneer in 2D printing like 30 years ago. So they're venturing into metal printing by doing a direct deposition of molten metal over a build substrate. And so, yeah, so let's put our hands into what fusion deposition modeling is. So FDM, so I'll be referring it as FDM for this presentation. So it's a method of additive manufacturing where you have a spool of plastic again. So that's it's called a filament, and it's being like extruded or pushed through a heated block of that has a exit nozzle of interchangeable diameters. So usually it's 400 microns to probably like 1200 microns, is like 1.2 millimeters. And then you extrude that over a path, which is being directed by a G code, which is again is a derivative of the slice that you took from the CAD model. And then you do that like for every layer to end up getting a final part. So if you see the images, the one on the left is actually the first or the base layer that you plot on the build platform. So the molten filament is being like deposited on that specific path, and then once that layer is done, the z-axis stage like moves down by the layer thickness or whatever your slice thickness is, and then you do the next layer like on top of the first layer. So after, say, if your entire layer is completed, you end up getting a final object as in image 3 on the right, far right. So there are pros and cons to this technology. So the pro, like let's start with the pro first. So it's cheaper, it's open source. So what happened was so Scott Trump's patent on this technology expired close to 2010, and a lot of the DIY community all over the world like kind of joined together and like created a very powerful open source platform for fusion deposition modeling called RepRap, Marlin, and so on. Like there's tons of open source research going on this, and yep, it's more accessible like for everyone. I mean, to simplify it more, you can probably get a printer for like, I don't know, maybe 10,000, 12,000 roughly, for a really good printer. So that's how the technology is accessible now, and also the material is cheap. The complexity is much less than what other technology needs, and also the post processing is it's extremely simple compared to what others offer. And coming up with the cons, so since it's a plastic heated filament which is being deposited. So you have certain restrictions on the size and the resolution that you can print on. So usually for the FDM, the layer height is roughly 550 to 500 microns, depending on your gantry. If you have a precision linear motor gantry, you can take it down to 50 microns. But that again depends on your plastic material and all its thermal expansion, all those material properties. Because if the material expands too much and or like contracts too much and creates warp, it's just gonna like fly off the mill plate. You can't print anymore. Just fail mid-build. And the next thing that's a limiting factor is the XY resolution. So say you have a really sharp knife edge that you want to print on the XY plane. So to put it into perspective, so XY plane is on the build platform, whereas like from the bottom left to the right is X and to the top is Y. So if you have a knife edge on that orientation and if you want to print that, so you're extruding a plastic through a round nozzle of X diameter, usually 400 microns. And then say if you want to build a knife edge, so you have to accelerate in one direction and then you have to decelerate and then accelerate in the other direction. So no matter what you do, you can never get a sharp point. It'll always be curved. So it's a drawback, but it's not super critical on what you can apply this technology to. So I've seen a lot of car companies and other OEM manufacturers using this technology to make their parts cheaper, faster, and on demand. So it's a pretty good and accessible technology that I guess maybe in like few years you'll probably have a FDM printer at your home, like everyone. So let's go to the next one. So I said, I mean, FDM, you have a filament that's being guided. So how do you do that? Like, so there are two basic motion control platforms for this. So one is the old school Cartesian, which is you have an X, you have a Y, and a Z, and then you coordinate this with a G code, and then you're done tracing your path, and then you do that for every Z, and then you get your 3D part. So what? People are crazy, so they come up with different technologies. So the other one is called Delta. So what Delta does is it's a triangle combination of a pivot. So depending on like the angular position and the height of 3 axis, which is oriented in Z, you can articulate the end effector or the heating block to wherever you want on the XY plane, XYZ plane. So it's kind of a core XYZ kinematic. So it's a little complicated to do motion planning and stuff, but it's extremely fast compared to X and Y because you don't have to deal with heavy accelerations and decelerations because the Cartesian that you see on the left, it should be super precise. So assume you have a gantry which is on a granite slab, and you have again a Z which is driven by a ball screw. So you have to deal with all the acceleration, forces, inertia to actually compute your motion path. If you don't do that, if you just do a point to point, you might end up getting artifacts on the print surface because of the resonance and the ripple that you get. So that's about the movement mechanisms. And the most important thing for an FDM is its extruder or the hot end. So what that is, it comprises of a rotary actuator, which is usually a stepper motor. I've seen servos in some cases. So what that does is it pinches or forces the filament against a grooved batting, which usually matches the filament diameter. So that ranges from 1.75 to 3 millimeters for a normal domestic application. So that the rotary actuator like forces that filament into something that's called a hot end. So that has a ceramic heating cartridge with a PID thermistor. So you set your temperature to whatever your material properties is. It's say 200 or 300 or 400. So I've seen printers which take it up to like 400 for some materials, which is like super tough and durable. So the motor just pushes the filament through that chamber. So what happens to that is you have your melting happening, and as you melt your plastic into a bottle, you force it through a nozzle which is 99% less than the diameter of the filament. So you have a 1.75 filament and you force it through a 400 micron nozzle. So you have a extremely continuous string or a bead of plastic, just like extremely precise. So it's a really key component of a FDM printer. Yep, and as I said, like the nozzle is not a fixed element. You can change it to whatever grade or dimension that you want. So there are filaments now which is just like kind of composite. So they have a chopped carbon mixed filaments. So those have really high abrasion. So you probably need a quartz studded nozzle. So you have a brass nozzle with the quartz crystal in it with the pilot hole drilled for the same diameter. So you force it through the quartz, so it's much harder. So it'll take up all the abrasion from carbon or whatever the composite that you add. So moving on to the next. Yeah. So the image that you see on the left is actually like one of the first FDM printers by Stratasys. So it's like yeah, it's a milestone in 1980. And then so once the patent expired, a lot of DIY people stepped in, and then like they took it completely to a next level, like making it extremely accessible and like open source, and pretty much anybody can do it without any licensing or patent fee or anything. So the image on the middle and the right are like one of the extremely early prototypes of open source printers. So it's made by a group called RepRap, which is repeated rapid prototyping. So their goal was to make a printer and print parts out of it, which is for another printer. So it's kind of a ever-going cycle. So it's like it's analogous to what they call lathe. So you use a lathe and a mill to make parts for another lathe and a mill, and then it keeps going on. And this is kind of the same. So you make parts for the printer, again, printable parts, not metal, printable parts from a printer, and then transfer it to another printer, and then go on. So the next technology which I'm extremely interested is SLA or DLP. So it's an interchangeable term, but SLA is what was coined in 1980 by Charles, and DLP is kind of a hybrid technology between what they used to do it and yeah, the overall term. So what SLA is a method where you get a 3D object by repeatedly like curing a photopolymer or resin at at every Z layer. So say you have a 1 millimeter height object sliced at 20 microns. So you have 50 layers, and then you get a 1 millimeter thick object of whatever geometries that you want. So the image that you see on the left, so you have a vat that's filled with this photopolymer. So and then you have a integrated elevator or platform piston. So you bring the platform all the way up, and then you have the photo initiating system on the top, which is nothing but a laser source, a galvanometer scanner. So we have a laser source that hits on two articulating mirrors, so that depending on where what angular position those mirrors are, so you can articulate that laser spot at whatever XY space that you want. So you keep doing that, and you get a 3D object at the end. So there was another counterpart for this same technology. So it uses the same thing, the same resin, the same platform, same elevator, but instead of using a laser and a galvanometer, it uses a DMD or a digital micrometer chip, which was a proprietary TI technology. So it's nothing but a mirror chip which is found in almost all new cinema projectors or home theater projectors. So it has a grid of probably like 8 million mirrors, and then you shine light on it, a collimated light, and then so depending on your image or the slice, the mirror is going to go on and off. So all the on mirrors will reflect light towards the build platform or the resin, thereby curing it, and all the off pixels will go hit a black body inside. So you keep again doing that, and you get a 3D object. So what's the difference between these two? So both print with liquid and same UV, and so what's the difference? So what happens with the laser is you trace a path. Say it's similar to what an FDM does. You keep tracing that outline and infill and keep going on. So that takes time. So say if it's kind of tied to what your what's geometry of your part in XY is. Say if you have a 10 by 10 millimeter part, so that if that takes X amount of time, and if you have a 100 by 100 millimeter part, so that's going to take like quite longer than what your previous time was. So what the second system does is instead of tracing its path, it shines the exact image all at once. So it took the complexity of that XY geometry completely out of the equation now. So you can rapidly image the same stack without tracing or requiring a scanning optics or a galvanometer to do that. So that's how this works. So usually, so they started with 365, which is a relatively far UV used to our spectrum, and then they migrated to a 405. So all this is in nanometers, which is just the wavelength of the light, which anything below 410 is considered UV, and above that is obviously the visible range. And then yep, you keep doing that, and so what this resin is, it's nothing but a monomer of uncross-linked substance. It can be anything like polyethylene glycol, acrylate, or something, and then you have you mix that with a photoinitiator, and then like a cross-linker, and then once you shine the light, it completely cross-links and becomes solid. So it turns from a liquid to a solid. So that's how you solidify the layer. And then you keep doing that like for all the Z, and then you get a 3D part. So the pros and cons of this system is that it's a little expensive to fabricate, and it takes more time to do the process work and tuning and getting the right print settings right. And also it's a little messy. So you print the whole thing in inside a liquid. So when your part is done and you take it out, it'll be like dripping wet. So you need to do a lot of cleaning after that to dry your part, and then to put it for a second post curing to cross-link it even more and like make it harder to the final exact material properties that you want. And then so it's not that common, but I mean I've seen this technology moving into the common household as well in the near future. So one of the drawbacks of this is since they use a resin which usually cures at 4 or 5 nanometer, which is very close to the visible light. So you need to enclose this whole printer in a UV blocking box or shield, so that any ambient light or sunlight doesn't get in and kind of completely ruin the print. So that's one of the major drawbacks. Not a drawback, it's kind of a constraint on how you can apply this technology. And so talking about like the pros, so this technology can print like down to, anywhere down to like 5 microns in Z to almost like 100. So that's like a huge range. And this was one of, I think DLP SLA is one of the most widely used technology in the research and the precision field, because you can print your knife edge with this, because your mirror size is close to like 5.4 microns, which is more than enough to make your knife edge. It'll still not be a knife edge, but it's much closer representation to what FDM can do. All right, so yeah, the next one is like pretty interesting. I did work on this for like a year before I joined 3D. So yeah, it's a really good technology. So it's extremely simple. It's kind of a hybrid between your inkjet printers that you use at home and office with a with an FDM. So FDM and a SLA printer because it uses material, UV curable material. Again, you have a UV light source to cure it, but you use a different deposition technique. So it's a hybrid of all these three. So its nickname is called Polyjet because it's polymer jetting. As a again additive manufacturing method where you have a UV curable material, which is usually the same material that you use in SLA, but it will have much less viscosity because you have to jet it through a head with like an array of nozzles, which is like several microns in diameter. So you need a material which is extremely low in viscosity so that you can jet it out at like precise timing without creating any surface tension locks. So it's pretty close to the SLA. So what do you have is so imagine so what happens in your inkjet printer at your house? So you put a paper in and you have a jet or an inkjet head that has a die which has several thousand nozzles, which is usually a thermal jet if it's an HP or a piezo jet if it's an Epson. So depending on that, so you put a paper in, and then this head goes back and forth on the shortest axis. So depending on where it is, when it's moving back and forth, it'll jet out this ink material onto the paper, and then say after like after a few seconds, you get your printout out, which has whatever you need or whatever you want to translate from your computer. So that's great. So what if you can, instead of jetting an ink, what if you can jet a photocurable resin and then have a following UV light, which solidifies it as soon as it falls on something. So that's how this technology started. And then so what they took is they took a inkjet printer, they removed all the paper rolling and registration assemblies out, and then they put a elevator platform inside. So what they did is they did like the first layer onto the platform, and then they brought the elevator down by a certain layer thickness, usually like 20 to 30 microns, and then did another layer. And then they kept doing this, and then say after like 10 minutes, you end up getting a 3D object, which exactly translates what you had in your computer. So that's how this technology evolved. So talking about like the Pro, it's really versatile on what it can do because say now you have a jet that can like jet out the material at the right time at the right point. So it's not just that. So it's not just the material. You can do more with that. So what they did end up doing was so similar to what your inkjet printer does, jetting out 4 different colors, usually cyan, magenta, yellow, and black. So what they did is they started jetting out 4 different materials. So it's usually say 2 build materials or 3 build materials and 1 support materials. And then depending on your programming and combinations, you can jet out a multicolors or however you want. So one kind of a drawback for this technology is you definitely need 100% density support below it, so that your next layer, when it starts jetting droplets, it has some base or rigid substrate to fall on and cross-link when the UV shines on it. So this technology needs 100% supports all over the overhangs. So overhangs are surfaces which doesn't have supports or a substrate below them to support the next layer that's coming on it. So now that you have a configurable 4-channel jetting, so you can mix and match the support material to wherever you want, and then you get a final part. Another good thing is this so if you see the image on the left, you see the support is the support is a material which is in white. So you see that kind of trapped between like an arch-shaped cavity. So how do you remove that? Well, now chemistry comes into play. So they designed this material so that it's photocurable, and at the same time it's soluble with a solvent or water. So once you're done printing this, you can dip it into a bath, and then all those supports just wash away. Like it leaves no trace as if it was printed without support. So that's a um, really good like method that you can do more supports with. And it's also a drawback at the same time because you end up wasting more materials. Say if you print, say if you want to print something like an umbrella, just like upright, then you need a ton amount of supports under the bell than the entire material that you're going to use. So the waste is really high on this. Yep, and yeah, and this thing can go down to like 10 microns to 100 microns depending on the material that you pick and use. And it's relatively faster and it's not that messy compared to SLA and DLP. Go on to the next. Cool. So, well, this is a fun technology too. So it's called binder jet. It's binder jetting. So it's kind of a hybrid of all the three technologies that you saw on the previous slides. So it has components from FDM. It has components from DLP. It has components from the inkjetting. So it's a mix of all these three. Plus, you have instead of having a bed of vat, you have a bed of powder. So what this does is so say instead of jetting out a material from the inkjet head, what if you can jet out a glue or a binding agent? So you say you replace that cartridge with a box of glue, and then you have an extremely thin layer of powder, say roughly like 15 microns thick powder, which is uniformly spread out, and then this inkjet can trace can raster and like put the binder droplets wherever it needs, and then the next layer can continue. So what the next layer does is it brings the powder from a reservoir station, and then using a doctor roller, it just like slides the powder over the previous powder layer. So it creates like extremely precise deposition, and then the binder jetting continues again. So you keep doing this for n layers, and then you get a 3D part. So again, adding a little more complexity to this, instead of just jetting the glue from the head, why don't you jet all four colors, CMYK? So now you can glue it and then add color at the same time, and then finally what you end up is getting a 3D part, which is like almost 100% color represent on what you want to do. So it's extremely good for people who do prototyping. They want to like visualize, or say if you have an idea, you print something and then you want to pitch it to investors. Like if you have something which is like a physical representation rather than uh, just taking your computer and an iPad and then like throwing some stuff on the screen and like showing, oh, this is going to look like this now, but this is a better way to like represent those. And yep, you get a 3D part which is in full color. But one of the major problems is you make the whole thing out of powder, so your porosity is on the roof. So how you process this is once you're done with the print, you take it out. It's extremely soft part at that time, and then you dip it into a perculant adhesive, which is similar to cyanoacrylate or like super glue kind of chemical. So you let that glue like percolate into these pores, and then you kind of solidify the whole thing into its hard structure. So that has its own drawback too. So since you're adding a really hard glue into the pores, you make the part extremely hard. Since the part is hard, you make it super prone to being brittle. So if you drop this, it's just going to like shatter like all over the place. So So this cannot be used for any mechanical or real-time applications. Yeah, it's just a kind of a representation or kind of a cosmetic use printer. And yep, the next tech is it's again a hybrid of a SLA printer with laser, and uses some aspects of the powder printer that you saw on the previous slide. So instead of jetting powder, what this does is it uses the same powder, well, not same, yeah, kind of same powder. Yeah, it's like usually nylon or some kind of a metal, like very fine metal powder, and then it uses a really high powered laser to melt that specific point, and then kind of use again the same uh, rastering technique as a FDM to trace its path, like do an outline, do an infill, do a final precise perimeter, and then it keeps doing that layer and layer, and then you get your 3D part out of a wide range of materials, like right from plastics to all the way to metals, like really hard metals. So the laser they use is like it's really really powerful, like usually in kilowatts. And one important problem about this is so generally the laser is focused on one specific point, usually the center of the platform. But say when your galvanometer scans it to the extreme corners, so you tend to distort the beam. Say if your spot looks round or circular in the middle, if you steer that beam all the way to the end, it's no longer a circle. It'll be like slightly oblique, becoming oval. So that will ruin your approximation on the geometry that you want to create. So what people did was add a kind of optics, which is called f theta. So it's a f theta lens. It's a really expensive lens they use to correct this distortion, to make that the beam on the ends as close to a circle as possible. It'll never be a circle, but it's as close to a circle as possible. So that's how they print metals. Like, so there's technology called direct metal printing. So they use this exact same principle to print directly on metal powder with a really high powered laser. And the metal ranges from a wide range of materials. So there's a huge range of titanium there. Like you can print on stainless steel, you can print on like tungsten if you want to. It's like it's a mix and match for what you're trying to achieve and the application of the project. And so this, I would say, the material is really hard. It's since it's porous, there are some materials which need to be sintered. So whatever you get out of the printer is the green part. So you have to put it in a sintering oven if it's a metal to completely cure it, or if it's a nylon like plastic, then you have to dip into some kind of a percolant to seal all its pores, and then make it more hard. So it's more hard, again more brittle because of that, and it's a little time consuming because you have to make sure that the powder that you deposit on the previous layer is exactly precise in terms of thickness that you want to cure, and also since the scanning optics, it's going to take a lot of time to cure the layer. It's not a one flash operation. So if you print one small part in the middle, it's extremely fast. But if you have a really wide part, which is extremely thin, it's going to take call it like 10 times the time to do that. And also coming to the post processing, it's a little more tricky because you need to like recycle as much as powder possible and put it back to the system so that you don't waste those materials. And also it's a little more messy, so you need a like highly trained and skilled people to deal with metal powders because they're like toxic sometimes if you breathe them. So it's super fine and can create all sorts of problems in your lung. And forgot to mention. So one of the best aspects on this printer is the So your part is complexity free when you compare it to printing, because since you're printing it, the whole thing submerged in a big tub of powder, so you don't need to model any supports or plan for that. So it'll be self-supported no matter what. So you have this densely packed powder all around the part to support everything. So you won't have any overhang at like any point. So it's a really good merit for this technology. All right, so the last one is a pretty experimental technique. So there was a startup in New York, Western New York, called Vader Systems. So they started thinking about metal printing, and then they wanted to use aspects of a FDM printer to print metal. So what they started was they built this really high induction melting heater, and then they passed in aluminum wire from a MIG welder feeder. So they used this, and then they passed the wire through that, and then started melting that aluminum and like depositing onto a build platform, and then tracing its path, creating a metal object. So, and then they started developing this technology, and then they moved to something called MST, which is magneto-hydrodynamic pulsing. So it mixes a jetting technique and the FDM principle of heating to jet tiny droplets of molten metal, exactly depositing it at whatever the space point they want to deposit to. So it's a technology still in development, and luckily, like that startup was bought by Xerox, and they've been moved to a extremely classified facility to like develop this technology. Hopefully soon. It's a less messy technique to print metal, because you don't have to deal with toxic powders or heavy machinery. It's much more simpler. So it's a really good and emerging technology that's going to come up soon. Yep, and yep, that's about it. All right, time for some questions.
Participants, if you're having any doubts or queries regarding the sessions, you can just clear it off now. You can speak with us, Mr. Adarsh, and we can clarify your doubts.
Hello, can you hear me?
Yep, I can.
Yeah, this is Professor Vijay. I'm working at KCE. I was just reading through the article about the development of lung scaffolds, the bioprinting solutions that were made by 3D systems, and it was a very path-breaking achievement, I feel. So can you just brief on the techniques that you used in those projects?
Yeah. So I'm one of the chief engineers for that. So I may not be able to give a lot of details because it's unpublished and confidential. But what I can say is I use DLP SLA as my primary technology, combined with a really high-tech biomaterials, usually hydrogels, made by, we have a big team of chemists here who we do this on a daily basis, like make materials, and we have probably like a team of 10 who just do cellulization and like taking all these scaffolds and then putting cells on them, and then like making the tissue whatever you read on the paper. Yep. So it's a really fun thing, and it is it's an eye-popping technology that's going to come out soon.
Cool. Thank you.
Yep.
So we are having a question here.
Yep.
Is the FDM machine designed for a single metal?
Mm-hmm.
That's one of the question they are asked in comment box.
So what was that FDM designed for? What exactly?
For single metal. Is
Sir,
the
good
FDM
evening.
machine?
My question is, whether for different metals in FDM, is it designed for a single metal, or we can use multiple metals in the same machine?
Oh, you mean metal? Oh, okay. So so you can't use metal directly on FDM because that's a completely different technology. Like the last slide I went through, the metal jetting. So it's not an FDM. It uses FDM concepts, but it's not specifically tied to a material. So since the heater or the induction heater they use is like it's variable, so depending on your melting point and your coalescence point, you can interchangeably use whatever materials that you want.
Okay, sir. Thank you.
Yeah, but I can say one thing. So I don't want to say if you can't use FDM metals with FDM, but there is a startup called Vucanson. They're coming up with a technology where you can print like lower melting point metals like tin, lead, and stuff directly on an FDM printer. So yeah, it's going to come soon.
Okay, thank you.
And one more question is, can metal 3D printing apply to titanium metals?
Yeah, sure. So if you look at 3D systems or EOS, so we have a really good portfolio of metals. So I mean, we have like few titanium grades on the shelf, but we do a lot of research in other materials for the U.S. Army and other like other spaces who need them. Like so we also do titanium for implants. So we need a metal which is to be inert and does not react with the immune system or create any immune response. So yep, we definitely can print a lot of titanium grades.
I have one more question.
Questions?
What is the accuracy of
Hello.
made? I mean, in microns.
Can you repeat that again? I got jarred.
What is the accuracy of the products that are made in microns?
Oh, which exact technology do you want the accuracy on?
Whatever. Let us say this FDM or metal printing.
Oh, so FDM and metal is the accuracy is higher. It's close to say 50 to hundreds of microns. But if you take DLP, then so I can say one thing. So we are currently working on materials that can be precise and accurate down to like roughly 30 microns.
Okay. Can these products be used in dynamic applications? I mean, where the strength requirement is very high.
Yes. So the parts that are printed on a direct metal printer that doesn't go through a sintering cycle. Yeah. So you can use it, but you do have limits because it's a coalescence of powder, so it's never going to be equal to what you get out of a CNC milled part. So, but it's fairly closer. But I guess now you have adaptive design techniques where you can map all these stress components out and then design like to make sure the stress is evenly distributed across the part. So you can still use this technology and achieve the same result, but it's more of a mix of printing and the design at the same time rather than just machining it. So yep. I mean, I would say it's much closer. It won't be exactly similar to a machine part, but yeah, it's closer.
Thank you. Thank you, Ernest.
Akash, we have one more question.
Yep.
What about the strength of the components that we produce using 3D printing?
It really depends on the technology that you use, the material, and also the orientation that you print on, and the orientation that you do a testing on. So, say if you print a dog bone on an FDM, and then you can print the dog bone in like 3 different ways. You can print it flat, you can print it on the side, you can print it vertical. So depending on where your layer is oriented, the strength is going to vary, because if you do the testing on axis on the layer lines, it'll yield much earlier compared to what will happen to the same dog bone which is printed flat. So the layer lines will act opposite to your tensile pulling. So it varies a lot depending on the orientation of the part and also the technology. So FDM is since it's molten plastic, it will hold really well. But if you print on SLA, your parts are extremely hard because it's a photocurable like polymer. So that'll take more. So the yield point on those is really high. The FDM is more elastic. The DLP printed parts are more hard, and it takes up more before it peels off or breaks. And for the metal, it's again like the same thing. So if you do print it on a direct metal powder printer, it depends on your grain size. Say if you use really fine powder and if your layer size is exactly mapped to that, you can get really good material properties, but it's not isotropic throughout.
Dr. Dhananjay, sir, I hope your question is answered. Is there anything else that you would like to ask, sir?
Yes, sir. Yes.
Dr. Dhananjay, sir?
Thank you, sir. Thank you.
Yeah, any other questions, sir?
Sir, which is the most cost efficient?
No, sir. Thank as I have asked about any other.
Can you repeat that?
Sir, what is the most cost efficient 3D printing process?
So cost efficient. I would rank FDM as first, and then followed by SLA. So your FDM is the capital cost for an FDM is lower, but you might have a little bottleneck when you print multiple parts. But if you take a DLP SLA technology, so your capital is a little higher compared to FDM, but your throughput is much higher. So say if you want to make dental implant, dental surgical guides and invisible aligners, so you can kind of print hundreds of them at once rather than one each time. So if it's throughput, I would rank DLP. If it is the capital, I would rank FDM as the cheapest.
Thank you, sir. I understand this is early morning for you, but you took time and you shared your information. Thank you very much.
Yep. Okay.
Sir, one more question.
Yeah.
Can we use composite materials? I mean, like aluminum.
You have a separate nozzle for nylon, and then you have another nozzle for whatever the composite that you want to use. It's usually carbon fiber, or it's Kevlar or fiberglass, and goes on. But I've never come across a printer that does like a metal composite.
Okay. Thank you very much.
Any other questions from the participants?
Good evening, sir.
Yep.
Yeah, I want to know about the titanium alloys. Any titanium alloys are there for the printing of the aerospace components right now, for the Airbus or anything?
Yeah, so we have a lot of materials. Like I'm not sure of the exact grade on top of my mind, but if you can check out the 3D Systems website, there's a category called DMP, Direct Metal Printing. So they have like a really huge portfolio of metals and materials.
And can you suggest the like 3D printing machines? Like we have the like 3D like FDM process, anything. Like what are the processes involved for the metal 3D printing process? Like SL, like lasers in laser one or selective?
Yeah. So it is selective laser sintering primarily. Yeah. So there are a bunch of steps. So selective laser sintering is like one of the most common techniques, and there's also electron beam melting (EBM), and there is also like inert gas deposition. So yeah, but the most common is selective laser sintering. So you have a really high power laser, you raster on a powder bed, and then you do that for X amount of layers, and then you get a part. Yeah.
Thank you, sir.
But check out DMP on 3D Systems.
DMP. Okay, sir. I'll be checking later on. Thank you.
Yeah, it's good. Yeah.
Any other questions, sir? I hope you have answered all the questions, Mr. Akash. So we shall wind up the session. Thank you for your time, Mr. Akash. It was an informative and eye-opening session for many of the participants, I hope. We hope to see you soon in another faculty development program or any other programs conducted by our department. Thank you once again for participating, Mr. Akash. And thank you, participants, for taking your time in the evening.
Having me.
Yeah, sure. Thanks, Akash. Yeah, bye.
All right, take care.
And I hope, yeah, bye. And I hope all the participants will be attending our session on Monday itself. It will be the same time, I guess. It will be from 3 to 4 or 3 to 4:30. So hope to see you soon on Monday, right? Thank you.